you have a finite number of points?
Yeah, something about finiteness, right? Like, if I had infinitely many points, the loop might never close up. I could go 1 to 2, 2 to 3, 3 to 4, 4 to 5, and I just keep going, the loop never closes up. But with these finitely many points, I just keep following the path, and eventually I run out of points, right? So I start at, say, 2, then I go to 5, then I go to 3. Well, I have to go back somewhere. I go to 2, 5, then to 3. Okay, so a symmetry will decompose into a product of cycles because you start at a place, keep applying the symmetry, and there's finitely many places, so eventually you come back to where you started. That's a cycle. Any other thoughts about this loop business? Why do they have to be loops? Yes?
That way, like, every number is taken, like, accounted for. Like, you don't end up with a situation where one number just disappears.
Yes, exactly. If you got to 2 and then there was no out arrow, then you just be like, I'm at 2, you apply the function, you don't know where to go. That doesn't satisfy our 1 in arrow, 1 out arrow rule. 2 has to have an out arrow. Yes?
You need loops because of symmetry, and like symmetry needs to be stable. And the last one was pretty unstable.
Sure. Stability. I like this. Yes, we will ponder that later. Symmetry should be stable in some sense, yes. So wherever you start, there's always an out arrow. You follow that out arrow, takes you to a new spot. You follow that arrow, out arrow, takes you to a new spot. Eventually you run out of spots, so you have to come back to where you started eventually. That's why you get loops. Okay, cool. Every symmetry is a collection of loops, or cycles. Okay, so now we'll define what we mean by a cycle, and we're going to write cycles down in a bit of a new notation. So mathematicians tend to use this notation where you write all the elements in a cycle and put them in brackets. So for this guy, right, so the cycle one, 2, 3, right? We're going to call that 1 space 2 space 3, with the understanding that when we hit the bracket, we go back to the other one. Okay. So what does this cycle do? As a function, it sends 1 to 2, 2 to 3, 3 to 1, 1 to 2, 2 to 3, so on, right? Okay, so it's an infinite cycle. 1, 2, 3, 1, 2, 1, 2, 3. Now, are there any music people in the room? People who play like piano or guitar? Or, yeah, all right, yes, solid. Is there anything that you notice about these loops?
They're like beats. They're like beats.
They are like beats. 1, 2, 3, 1, 2, 3, 1, 2. That's a waltz, right?
Time signature.
It's kind of a time signature. Any other things you notice about this? Any other things? Right. One thing that stands out to me is that we could start this at different places, and we would still have the same beat. So we could go 2, 3, 1, 2, 3, 1, 2, 3, 1, right? We'd still be waltzing, right? Or we could go 3, 1, 2, 3, 1, 2, 3, 1, 2. Still the same thing. We're still counting 3 beats to a bar. I should actually, next time I give this talk, I'm going to waltz in it. Anyway, so the observation is that this cycle, we can conceptualize it in several different ways. So we can call this the 2, 3, 1, 2, 3, 1 cycle, right? And that amounts to starting the cycle here, saying 2, 3, 1, 2, 3, 1. Yes?
Would you say 231 maps 2?
2, 3. I would say that these are equal as functions.
Okay.
I'd say that it's the same function.
What does maps 1 mean?
Oh, right, yes. So maps is the way mathematicians say the following thing. So if I plug 1 into my function, it should output 2. So I would say my function maps 1 to 2. Or, yeah, mathematicians love this kind of stuff. Everything in math is basically a function. As you take more math courses, functions will just grow and multiply, it'll be crazy. So we say the function maps, the function transforms, the function takes. There's lots of verbs for this. But okay, so 1 goes to 2, 2 goes to 3, 3 goes to 1. Okay. So as functions, this cycle is the same as this cycle is the same as this cycle. They're all the same function fundamentally. Right? If I write if I write this version of the cycle, that's the same as this version of the cycle. What I've done here is I've just rearranged the columns of this table, but fundamentally the function is the same. Okay, so this is a tricky point. Are there? I remember when I was taking this course, I was like, what? How could there be 2 functions? But are there any questions here about this? Yes.
So are you saying that you can rearrange the column with any other kind of function like that?
Yeah, you can switch any of these columns, and as long as the columns stay intact,
That's legal.
as long as the columns stay intact, you're talking about the same function.
Okay.
Yeah. Yes.
Could you assign an equation for this function?
Yes, certainly. Yeah. There would be a like y equals mx plus b kind of thing that does this. Yeah. But yeah, there's totally an equation there. So maybe that's a cool exercise. Try and find that function. Okay, so these cycles look different, but they're sort of fundamentally the same. Those all represent the same cycle. Okay. Right, so we'll come back to our example of a rotation. Now, in this notation, 3 goes to 1, 1 to 3, 3 to 2, 2 to 1. Oh, oops.
It should be 1, 3, 2.
Actually, that's a typo. Someone's paying attention. Sorry, this is the counterclockwise rotation. Right? 1 goes to 2, goes to 3, goes to 1. Yes. Typo there. Okay, there's our reflection. You can write this as a product of cycles. So we've got the cycle 1 to 1 to 1 to 1 to 1 to 1 to 1. Then we got the cycle 2 to 3 to 2 to 3 to 2 to 3. Okay. And now, to come back to our symmetry, we can decompose it into its fundamental cycles, its fundamental parts. Right. And what we do is we list off each of the cycles that we see there. So try and write down on your paper the cycle decomposition of this guy. So try and write down with these brackets.
get the cycle?
I believe so.
Where is it?
Not sure if you can read it. Maybe the whole small.
I don't know, I wasn't paying attention. Bob, does he have a cycle right now? I was drawing.
You can write it instead of having it as one big cycle, because you can't write it as one big cycle.
Oh, right.
You have to do this three, yeah.
Right, okay. Wait, is it about commas?
Math 301. So this is groups and symmetry. Are you a math major? Minor, cool.
But I didn't do 2, 4, 6 and 2, 4.
Oh, 2, 4, 6 is like proofs, right?
Yeah.
Uh-huh.
But one of the group leaders is a math major.
Oh, cool. That's great.
Are there supposed to be commas when you do the...
You can do commas if you like. Everybody does. Alright. Who's got it? Who's written something down? Okay, I'm seeing lots of tentative hands. Okay, yeah. Assertive hands, good. Okay, sweet, we've got something.
Okay.
So let's write this guy down. So there's the 1-4 bit, right? That's this cycle.
I got that.
Then there's the 2-5-3 cycle.
I also got that. I'm smart.
So far, so good.
Of course.
Okay, yeah. And then there's the 6 goes to 6 cycle.
Boy, I told you I'm really smart.
Right. So did everybody hear that
I'm very
question?
smart.
Yeah.
I got it.
Okay, the question was, does it matter what order you write them down in? Interesting question. It turns out that because none of the numbers are in common between the brackets, they all sort of treat each other independently, right? There's no interaction between these two guys. These guys deal with 1 and 4, these guys deal with 2, 5, 3. So you can switch the order. Yes?
And also, it's a product of cycles, right?
Yeah.
So multiplication doesn't really matter where you put the terms.
Right, so here we can switch the order of those guys,
There's no sense.
right? And that'll produce the same product of cycles. Okay. Yes, so,
I meant more like instead of 2, 5, 3, you write like 3, 2, 5.
right. Oh, right. 3, 2, 5. Yes, that would be equal. You can write 1, 4 or 4, 1. Yes.
With like 2, 3, 5 words, I think it's in the.
Not 3, 2, 5.
It would be 3, 2, 5.
Right? You can't move it.
Yeah. Let's just write down what we're talking about. So we have it.
2, 6, 7
The song never leaves.
Right. So 2, 5, 3 is the same cycle as 5, 3, 2. Okay. Alternatively, it's the same cycle as
3, 2, 5.
These are all equivalent ways of writing this guy down, depending on where we start. Yeah? Okay, so when we're writing down a cycle, when we're writing down a symmetry, when we write down a symmetry, we have a fair bit of flexibility. We can move the terms around, and we can cyclically reorganize the stuff inside. Okay, so we can switch these two guys, and we can cyclically remove the stuff inside. Mathematicians tend to not write cycles with one number. Okay, so if it's just 6, 6 goes to 6 goes to 6 goes to 6, we tend to not write that one. Okay? So there's several different ways of rewriting this. Like this. Okay, so it looks like I've definitely bored like 3 people to death with all this theory. Don't worry, we're almost at the hardcore application. Okay, so fundamental theorem lecture, the fundamental thing I wanted to tell you about today. Any symmetry can be written as a product of disjoint cycles. Sounds like Greek to me.
Are you all right?
Yes. Just should have moved the chair earlier.
I think she's good at that.
Okay, so
Something about symmetry.
yeah, so
It wasn't symmetrical.
okay. So this is sort of our kind of our fundamental idea for the talk. And I want to point out that when you encounter a math statement, it's often written the most concise way possible. Okay, mathematicians tend to be extremely lazy, so they don't write any more than they really need to. So this is a very compact statement that summarizes a lot of what we've talked about today, and it has some new words in it, right? This word disjoint. Okay. Has anyone heard this word before? Okay, a couple people. Good.